Hello everyone, I hope you're doing alright. In the last episode, we learned what logic gates are and what we can do with them. In this video, we're going to build the probably most uncomfortable to use calculator ever made. But at least it'll be able to add two 4-bit numbers. This means we can add two numbers between 0 and 15. But how are we going to do this? For now, we only have the gates, which can do some kind of logic, but certainly not add or subtract numbers. In fact, how can we even represent numbers if we only have on and off, or 0 and 1? Normally, we count from 0 to 9, and then we go one step higher, increment the 10th place, and redo the same steps. In a decimal system, we have 10 digits to work with, and the math behind every place looks like this. We have 10 digits, so we just add x times 10 to the power of 2, plus y times 10 to the power of 1, plus z times 10 to the power of 0, and we get our result. Now, this may look like we just made math unnecessarily complicated, and we did. But now, what happens if instead of 10 digits, we only have 2, 1 and 0? The math would look like this. So we have x times 2 to the power of 2, plus y times 2 to the power of 1, plus z times 2 to the power of 0. And there we have it. We created our own system to represent numbers using only 2 digits, and this is so-called binary. Now we can continue this to our needed 4-bit. Let's say we have 1010 in binary. We can convert that to decimal, so we as humans can better understand its value. So what we do is simply add 1 times 2 to the power of 3, plus 0 times 2 to the power of 2, plus 1 times 2 to the power of 1, plus 0 times 2 to the power of 0. And the result is 10. But don't be confused, because this is a 10 in decimal and not a 10 in binary. To better distinguish between these two formats, let's add this index so we know what we're talking about. Now, we know how to represent numbers with only zeros and ones. And in Minecraft, we only place 4 lines next to each other to represent the 4 bits we have for our numbers. What we can do now is to place another 4 lines next to those, and we have our second number. But how can we add the numbers now? We can't just connect the wires and expect it to work, because as we can see here, 10 plus 10 would be equal to 10, which is obviously wrong. Let's take a step back and think about how we add numbers in decimal. At first, we start with the digits to the right and add them. Now, we have 2 possible outcomes. Either we get a number with only 1 place and everything is alright, or we get a number with 2 places and we have to carry the higher place to the next step. Now here, we have 3 digits we have to add, but still the same possible outcomes. Either it's going to be alright, or we have to carry a digit. We can also think of it as if we are always adding 3 numbers, because it doesn't matter if the carry is a 0. So let's do that with binary and see what happens. Let's say we want to add 0111 and 0110, or 7 plus 6. We write down the number and start to the right. 1 plus 0 equals 1, so we can simply write that down. And let's also say that we carry 0. Now, on the second place, we add 1 plus 1, which is equal to 10. It's not 2. This doesn't exist in binary, but a 2 is equal to 10 in binary. So we write down the 0 and carry the 1 to the next place. Now, here we have 1 plus 1 plus 1, which is equal to 3. But again, we don't have a 3 in binary, so we have to use 1, 1. So we write down the 1 and carry the 1 to the next place. At last, we just have to add 1 plus 0 plus 0, which again is an easy 1. Now, we have 1101, which is equal to 13. And that's great, because 7 plus 6 is indeed equal to 13. So now, we only have to figure out something to automate this process, so we don't have to do that by hand. So let's again start off easy. Let's say we want to add 2 bits. Let's call them A and B. We then have 4 possibilities. Both are a 0, one of them is 1 while the other one is a 0, or both of them are a 1. If we put this in a table and add the outcome, we get a so-called truth table. We have the inputs A and B, and the output carry and sum. let's have a deeper look at the outputs. Let's start with the carry. As we can see here, the carry is only 1 if both of the inputs are 1. That's interesting. If you remember last episode, that sounds a lot like the AND gate, because only if both inputs are on, then the output turns on as well. Let's keep that in mind and do the same thing with the sum output. And this time, it looks a lot like the XOR gate, because only if one of the inputs is on, while the other one is off, the output turns on. Now that we know that, let's get back in the game and construct something like that. What I've done here is that I've put an AND gate next to an XOR gate and connected the inputs to one another. Let's see if it does what it needs to do. If A and B are 0, the sum and the carry are both a 0 as well. And if only A or B is a 1, the sum turns to a 1, but the carry stays a 0. And only if A and B are a 1, the sum turns to a 0 and the carry turns to a 1. And that's great. We can now add two numbers from 0 to 1. Okay, I admit this doesn't sound that great. But at least we made Redstone calculate something for us. This is called a half adder. So let's write that down and save it for later. In the real world, this would be equivalent to use electricity and make it calculate something, which is exactly what the device you're watching this video on does right now. This video is nothing different than a lot of zeros and ones. But we're quite a step away from that, so let's continue our journey. The next logical step would be to put 4 of these half adders next to one another. But wait, something's not right. If we take a step back to the theory, we should be able to add 3 bits, because we have 2 bits and the carry. So I made this circuit. It looks a bit intimidating at first, but it's not that hard. At first, we have our half adder here, which still adds our bits A and B and puts the answer here. Now I put another half adder here to add our carry in to the sum of our first half adder. And last but not least, I put an OR gate and connected both carry outputs to it to create a new carry out. Let's see if this works. If all inputs are off, the outputs are off as well. If only one of the inputs is on, only the sum turns on while the carry stays off. If only 2 of the inputs are on, only the carry turns on and the sum stays off. And if all inputs are on, the sum and the carry turn on. That's great news, because it works as it's supposed to. This is called a full adder. So let's write that down and save it for later. The last thing we have to do now is to put 4 of these in parallel and let the carry ripple through. This means that we connect the carry outs to the carry in of the next place, which looks like this. But does it work? Let's put our example in here. So 0, 1, 1, 1 and 0, 1, 1, 0. And the output is 1, 1, 0, 1, which is correct. Now that's really nice, because we just made Redstone calculate something for us. Of course, this isn't a hard math question, but you could just make this thing longer and add more full adders to add more bits. So you could make a gigantic adder, which would probably be faster and more reliable than you. No offense. But for our needs, we'll continue using only 4 bits. But if you want to build a computer with 8, 16 or 64 bits, feel free to do so. This is called a ripple carry adder, but let's just call it an adder for now. But before saving it, I built another version. This has the same functionality as before, but I put 2 of the full adders above the first ones just to make things more compact. And now we can save it for later. Now we can already add numbers, which is a great milestone on the way to build our computer. But we'll continue our journey in another part. I hope you enjoyed the video and learned something new today. If so, please consider to like this video and subscribe to the channel to not miss any future videos of this series. Also, if you want to leave me some feedback in the comments, I would highly appreciate that. So, until then, goodbye.